Are there any more whats?
I would have had perfect attendance, but his wife kept me.
My wife. And if that's all, then it's not a problem. Okay, we are starting here. I have everyone here, but Bryson is okay. So in lab yesterday, what did you learn?
I learned that working together as a group gets things done faster.
Working together as a group gets things done faster.
That the Rocky Mountains were formed in the Permian period.
Okay, the Rocky Mountains were formed in the Permian.
Yeah.
Looking at the grades, there were a few things that were disconcerting. And, I drew all but 3 of the lines. And only 1 or 2 people had the rest of the lines correct, which means that I did way too much and didn't give you enough chance to figure out what you're doing.
Can you repeat that? Oh, how many people got the lines right?
I only like 1 or 2.
No.
I don't know who it is. I'm not pointing fingers. I wouldn't.
Wait. No, I
But-
only put 1 more in because I couldn't figure out any of the other ones. I figured out one other one that you did.
So let's look at that real quick. Of course, this was not part of my lecture plan. It was just where I started with from lab, reviewing it.
You didn't put which one you got it wrong.
That's true. It doesn't say which ones you got wrong. It just says how many. That's somehow geology.
So do we have to look at our grade on Moodle to know?
No, it actually doesn't tell you, but I'm going to go through right here to finish it out.
Okay.
And I just erased 1 too many lines, but that's okay. I can put it back. So what was the method for choosing how to draw these lines?
Based on which layer appeared between which layer.
Okay, based on the order of the layers.
Yeah.
So there's what we had that I drew for you. And we only had, I think it was 3 lines left. So what we need to do is see where there's missing lines where we have layers that aren't accounted for. So the easiest one is there's no line going to the D here, right? Between the D and the C. So we know we're going to need a line there. So we come and we say, well, D, C, how do we have any D or C with respect to Z? So here we have BCM. Here we have Z is above D, but we don't have C. Here's. So since we know that Z is above D, that tells us what we need. Well, that we need Z is above D. So I'm gonna put in black the new lines that I'm doing today. If I can get this thing in an orientation that I like. And there I moved the wrong thing.
No. What did I do?
I'm trying. There we go. What? So there Z is above D. And then I was looking for the line between these two. Well, this must also go like that. Right, because both C and D are missing between the L and the Z there. So that's 2 additional lines. And where's my last missing line?
Your last one is from C to Z.
Yes. So C is below Z. And so I should have a line like this. And so now if we look at this, we should see the right sequence in all of them. Now remember, we have S and P are below here, and P is below here and here. And so we have P, S, ML, missing the C, D, Z, missing the B, X. Right, so we can look at these and read from those arrows ones that are missing. Now, if there's something missing in two adjacent columns, we're not going to be able to get it in there because it's missing in both. So that's how it should have been finished. So those were the 3 lines I didn't draw.
You didn't mark anything off online. How am I supposed to know what I got wrong? You're supposed to look at the chart that you just.
Yeah, look at what I just finished here.
But other things, or was that the only thing I got wrong?
Well, on the front page, it should have everything. Oh, I'm sorry. On Moodle is the graded one. That's just stapled together what you turned in. That's not the graded one. I'm sorry. I was confused at what you're looking at. Okay, so do you understand a little better what you were supposed to have done there?
So I wasn't supposed to put a line here.
Because
Technically it means the same thing. Mine was right.
Actually, that should be okay.
Oh, that's okay. So that's, I think, the only thing that I don't know how to see my grade. But.
Yeah, that actually should be okay.
Oh.
Send me a note or email or something to fix it, okay?
Can I do a note?
Yeah, just make sure that I get it to remind me. Okay, otherwise, how did yes?
So for layer X,
Mm-hmm.
it didn't have reptiles in it,
Yes.
but it's above B. Would it still classify as Permian?
It's going to have to be Permian because it has to be younger than the layers below it. And since we had a Permian layer below it, it's either Permian or after the Paleozoic. So assuming it's in the Paleozoic, it's going to be Permian. And that reminds me, I was going to tell you, and so I wasn't going to take off because I forgot to tell you, this one here is pre-Cambrian. And I meant to just tell you that. I didn't, but everybody did it anyway, so that was good. Maybe Nathan told you, I don't know.
No, we were paying attention when we were going over Precambrian and Cambrian and all that.
All right. So the fossils, it was somewhat surprising to me that I told you that there were 3 answers there in number 4. And I think everybody put more than 3. That surprised me a bit. But
Sometimes we're good students and overachievers. I thought we were done with this.
so the ones that were indistinct, I would have to sit here and go through all of them to remember which ones they are. There was, I think it was S, L, and D.
How was it S though? S
Okay.
was clear.
You're right. S is clear. Yes, so you're right. It wasn't S.
C, D, S, and C.
Well, there's only 3, remember?
No,
So it was
there
L,
four.
C, and D.
There was 4.
No, there were only 3.
Wait, what's the question?
There were only 3
Like 5.
that could have spanned more than one that you couldn't distinctly say it has to be in this one.
Although, and I think you could see
Well, maybe, I don't know. Maybe we got one wrong, but.
Okay, well, let's get going with the lecture portion here. I just want to go over that a little because I was a little disconcerted looking at the reports. So we're going to talk about the ocean today. How much of the Earth is covered with water?
75,
85. 90.
The correct answer is 71%, but I would be totally happy with 70%, right? We're not looking for exactness here. So 71% of the Earth is, we look at it like this, we tend to think, well, that's a lot of Earth. But actually, looking at this picture here, how much of the globe would you say is roughly covered with land versus how much is roughly covered with water?
50.
Yeah, I would go with around 50-50 as well. And if we look at this one, this is still the same globe. It's just looking at another side. You know, that's like 80 or 90, probably 90% water. And so it's easy to see if you look at the entire globe, yeah, it's mostly water, 71% water. Something else that we never think about. In fact, some people think that it's not something we should talk about. Where do people live on the globe?
On the land.
Mostly on land is a great answer that I thought of as soon as I said it. And I was like, I hope nobody answers that. It's perfectly correct answer. If you look at the equator, we have people that live here and, of course, on the islands. And we have people that live here. And let's not forget those regions. How much of the continental mass is that where people live below the equator? It's not very much. So it's somewhere between 10 to 20% of humans live south of the equator, and 80 to 90% of humans live north of the equator. Now, I have seen people who get very upset about this. They say we live in a north-centric frame of mind, that we believe north is better and south is worse. And so when we make maps, we put north at the top, and we're putting, the people we consider more important on top.
No.
Yeah, I would say no, that's ridiculous. But I've been in people's offices, other professors, who have a picture of the map upside down because they think that it's showing some favoritism to have north up.
What?
That's really dumb.
Doesn't it that's how it's positioned in space though?
Well,
Well,
it's arbitrary decision.
No, up.
That's true.
Here is the way we actually come up with north being up. We use what we call the right hand rule. We wrap our fingers the direction the earth rotates, and the direction the thumb of the right hand points is what we consider up. And so that's why north is up.
Down there it would be.
No, the earth is still spinning the same direction.
I mean, so
If you use your left hand,
wouldn't
You
it be
get
pointing down? Like if you were in Antarctica, it would be pointing down in the direction of.
no, because the earth is still spinning like this, no matter where you are. So if you take the right hand and you indicate the direction the earth is spinning. It's kind of like one of the greatest, I may have mentioned this or may not have. There used to be a TV show called Street Smarts, and they would ask people on the street a bunch of questions, and the contestants had to guess. One round it was how many got it right, in one round it was, two people got it right, which one got it wrong. And it was stuff like that. It was kind of funny. And the best question was, in the northern hemisphere, the sun rises in the east and sets in the west. Where does the sun rise in the southern hemisphere? Yeah, because the earth is rotating that direction. That's why the sun rises in the east. It's not the sun moving, it's the earth rotating. As the earth rotates, we're rotating so that the surface of the earth is going like that. And hey, look, there it rises. 1 out of 3 got it right for that round, which is funny. Okay, so it's the same thing. We're rotating the same direction, northern, southern hemisphere. And now this is going way off topic. I saw an article yesterday where a professor said that being on time is racist. Because if being on time had a color, it would be white. Yeah, that to me made as much sense as saying that it is, racist to put north at the top of a map. It's drawing equivalences that aren't there.
Wait,
How is
be
time
not on
right?
time?
Being on time, she said, is a white trait.
Just saying that.
It's a what trait?
It's a white trait.
Yeah.
And so being on time, therefore, is racist.
That's funny. I've actually heard that, but I was raised in the ghetto, so
It's racist for what?
that's what they say back home.
Racist, well, okay. But we're not here to talk about racism in general. We are here to talk about politics. That's no. So it obviously makes sense to learn a little about the ocean and the atmosphere. And so this chapter is about ocean and atmosphere. And surprisingly, after setting the table with the ocean, it starts in with atmosphere. And something that is a little surprising is, according to scientists, the atmosphere we have today is not the atmosphere we've always had. Oh, really? Okay. So we talked about that with regard to dinosaurs and extinction events. But that is minor changes in the atmosphere. when we say this isn't our original atmosphere, we're talking about major changes. So now, once again, this is the scientific theory for the history of the Earth. So it may not match with a creation by divine caveat. That is, that there was nothing and then God created the Earth as it is. But the scientific view is that the Earth formed from materials with high melting points sticking together. But of course, we talked about the nucleosynthesis and that hydrogen and helium are by far the dominant gases that were made in the Big Bang. And so you would have had a lot more hydrogen helium gas at the first formation of the Earth, just because together that makes over 99% of all of the material that was available in the solar nebula. So the first atmosphere would have been hydrogen and helium. Okay. Can you breathe helium?
No.
Well, you can. It's kind of like the meme I saw. All fungi, or fungi, however you want to pronounce it, can be eaten. Some only once. Yeah. So helium, you can breathe helium, and it doesn't kill you, but you need oxygen. So, have there been documented cases of people dying from breathing helium?
Yes.
Yes, there have. Have any of those cases that are documented been because they were breathing in from a balloon and making their voice squeaky? No. There was a case a few years back where some parents tried to claim that's what happened with their daughter. But every case has been a case where something stupid was done, like taking a big balloon and putting it all the way down over the shoulders and breathing pure helium until they suffocated.
Did the kid do it? Or straight to the kid?
No, that was a person who was drunk at a party. Yeah. Usually alcohol is involved with these helium deaths. Okay, so helium wouldn't kill you, but it wouldn't supply the oxygen you need. Hydrogen, same thing. So I'm glad we don't have that initial atmosphere. Now, why don't we have that atmosphere? The answer is actually kind of interesting. The Earth's gravity isn't strong enough to hold on to hydrogen and helium gases. Because they have low mass, they travel at a high speed, higher than the 11.2 kilometers per second. That's the maximum speed for things for the Earth to hold on to. If something's going faster than 11.2 kilometers per second, that's fast enough to get from here to Omaha in about 5 seconds.
I love that.
Yeah, it would be nice. But if you were going that fast, you would escape the Earth.
Well, 6 seconds.
Hey, as the crow flies, which is what you would be doing in that case. So hydrogen and helium, the Earth can't hold on to. And that brings up a question. How is it that we have hydrogen and helium if the Earth can't hold on to it?
Because we have a lot of it.
Okay, we started with a lot of it.
And we lost some of it.
We lost almost all of it.
And we still have some and we're still losing it.
Maybe it's trapped between a lot of the other gases we have.
Okay, trapped in the Earth.
Yeah.
Hydrogen and helium are both constantly being made by radioactive decays. We've already talked about radioactivity, and we talked about things like alpha decay. What is an alpha particle? It's a helium nucleus. So helium is being created with alpha decays. There are also decays that kick off protons. Well, that's hydrogen. And so these gases are actually being replenished due to radioactive decays, but in small amounts. Secondary atmosphere comes from outgassing of hot rock. So you have things like volcanoes. In the Hadean period, the Earth was a very hot, molten place. Lots of volcanoes where things froze because it's basically a melted Earth still. And so you're going to have all of these hot, molten rocks giving off the gases that were trapped in them. And so that's the secondary atmosphere. The tertiary atmosphere comes from, scientists believe, I need to get my highlighter. Comets. What is a comet?
A big rock from outer space.
Halfway true.
A star that has fallen.
No. you were more correct with the first one.
That would be.
Comets, we think of them as ice balls. They do have some rock and some ice.
So there's water and space. Is there aliens in space?
Yes.
Are there aliens in space?
Oh, yes.
A little off topic, I'm just going to go with Ellen White saying.
Yeah.
Okay.
Angels,
But, like-
angels are aliens.
Do you believe?
Well, no, not just that.
Well, that too. Well, yeah, I'm just
Do
like.
you
adding
believe
that.
we could contact aliens before Jesus comes again?
We count angels? Yes.
I do not think it's going to happen, no.
But do you think it's against the writings of the Bible, if you will?
I do not, but I do think that I should move on with class and not discuss it. So the comets are basically ice balls out there. So when you see a comet in the sky, it's an ice ball that's come too close to the sun, and it's undergoing sublimation. That's a word that we just learned. What was sublimation?
Drastic change in quick speed.
Going from is it going
It
from
is a
solid
drastic
to gas?
Going from solid to gas. So you have these ice balls that, because of the sun, are going from solid to gas, giving off gas. And as it gives off gas, you have little pieces of the rock and stuff that will also come off. And so you have a dust and gas cloud. And then sunlight scattering off of that dust and gas cloud is the tail you see on the comet. Well, if a comet hits the Earth, all of its ice and stuff will then be part of the Earth, and it's believed that's where our water came from. That sounds pretty fantastic when you think about how much water we have. But there are a lot of these icy bodies. Take, for instance, one of the bigger icy bodies out there, Pluto. Pluto is not considered a planet anymore. Why? Because it's nothing like the planets.
It's still done.
It's still not. So
It's a
the planets, all of the planets, all 8 of them, have a big rock. And the planets that formed beyond what we call the frost line, where it was cold enough for these volatiles to freeze, for things to stick together, have lots of these volatile things. And you go out far enough and you get things that are ice balls. And so if you look at Jupiter, Saturn, Uranus, and Neptune, all of those have a big rock at center and then a lot of gas material around them. What was the dominant gas according to what I said 5 minutes ago? Hydrogen. And so you have huge amounts of hydrogen actually in the liquid form around Jupiter and Saturn. Excuse me? Well, yes, it is. If you go farther out to where Pluto is, Pluto does not have a big rock in it. It is maybe some small rock and a lot of ice. How do we know this? We do.
Have you been there?
Have I been there? No, I have not. But we did send. Did you say submarine?
No, has someone.
We did send a probe, the New Horizons spacecraft, about 3 or 4 years ago. I don't remember the exact date.
And it just got
And it passed by and took some pictures, so we now know way more about it than we did 5 years ago. But we get that it's half rock, half ice, roughly, by measuring its density. And you might say, how do you measure the density? You measure the density by measuring its gravitational force on things and measuring its size. And so we are very confident in its density, and its density is around 2 grams per centimeter cubed. All that had a density of 1 gram per centimeter cubed.
Oh.
Rock has densities in the ballpark of 3 to 7 grams per centimeter cubed. So it's somewhere between rock and water.
But it depends on the rock.
It does depend on the rock, that's right. But no rock has a density as low as 2. And so it is estimated to be about half rock and half ice. And that's only an estimate because we don't know exactly which rocks they are. And we don't know which ices they are because it's not all water ice. Now, after we got this stuff from the comets, things like water, then we have to have photosynthesis by cyanobacteria. What are cyanobacteria? Who's been to Yellowstone? Okay, so at Yellowstone, you have these hot lakes, if you will. And when you look in those lakes, they've got all kinds of pretty colors. Those pretty colors are because of cyanobacteria, bacteria that can live in a very harsh temperature. And actually, they're pretty specialized, can only live in this temperature, and nowhere in between. So you can actually kind of tell the temperature of the water by the color of the cyanobacteria. But photosynthesis in those created the oxygen that we breathe. And so now we have our, get back to a pen, roughly 71% oxygen and roughly 71, that was wrong, nitrogen. And it should have been 79% nitrogen and 21% oxygen. That's the atmosphere that we have today. In different times in history, they believe the oxygen percentage might have gone as high as 30%. If the oxygen percentage is higher, well, it's going to make life different for us. If it's lower, it definitely makes life different for us. With my new house in Colorado, I've determined this, for myself. Now shifting back to the ocean. That was a quick overview of the sky, now the ocean. Actually, let me ask you, I was reading through the recommendations on how to treat these topics. And one of the recommended things is ask students a question, and that question is, where does the material that forms a tree come from?
The form of a tree.
Yeah.
It comes from the ground and the tree.
Okay? The typical answer that people give is the ground. But that's actually not the correct answer.
From the seed.
Not from the seed. The volume of the tree, you put
Water.
all that in the seed.
I just said the ocean.
Water is bigger. The sun.
No. I want things that are on Earth. Okay, if you say from the sun, you're hoping up.
The sunlight. The seed, the sunlight, the
It actually
water.
comes from the air. The tree is getting most of its nourishment and the stuff that it builds itself from the air. It does get moisture from its root system and some small amounts of minerals.
So you can grow a tree in a vacuum if there was dirt and water.
You could not.
Sunlight.
You could not. You would not have the photosynthesis. Because the photosynthesis is a process where gases in the air, namely carbon dioxide, are processed, and it keeps the carbon. It discards its waste product of oxygen, which makes us really happy because for us, oxygen is what we need and carbon dioxide is a waste product. So we have a symbiosis between our needs and the tree needs. But it's getting much of its nourishment from the sky. It clearly is getting water, though, from its root system. Okay, so getting to the oceans now. Here's a picture, a graphic that is clearly compressed that illustrates how the oceans look. Now, the oceans are vast and largely unexplored. I have always held that before we worry about trying to send a man to Mars, that we should figure out technology that allows us to make, like a community living on the ocean floor. Right? The ocean, 71% of the earth. If we could live underwater in the ocean, we would have much more room for expansion for society. It's a very hostile environment, though. But then again, on Mars is much more hostile. So, looking at the ocean, you have, of course, the coast. You guys know I'm from California, grew up in Monterey Bay Academy. I love the coast. You go out and you have this continental shelf. Notice that this is, compared to the grand scheme of things, a fairly thin shelf. It's not very deep water. And then you have the continental slope, which our textbook says that's where you shift from being on the continent to in the ocean. The continental rise then continuing on. Normally a person would say right here is probably the boundary because it shows ocean crust and it shows continental crust and where the two meet. That's where I'd probably say the boundary is here. So this picture is probably a little missing the point, a little deceiving. And here's something that normally happens. It's not happening in California right now, but normally what happens when the ocean crust and the continental crust meet? You do have this stuff that got pushed up here, right? This stuff here. But what usually happens? What happens with the ocean crust?
It slides underneath the continental crust.
Yes, it goes like this. It subducts. And keeps going down, gets melted and reassimilated into the mantle. So that ocean crust is going to become part of the mantle again. So we're recycling. This doesn't show it subducting. Maybe the person who did this was thinking of California's coast, because right now, California, we don't have the ocean subducting under it. We have a transform fault. We have the ocean is sliding north against the continent. Okay, so we keep going out. Something that is shown here that's fun is the deep sea fan. What does that look like? Okay, it looks like a fan. Yeah, good reason to name it that. But what do you think caused it? Yeah, this is caused by a stream or a rock slide. It looks like a delta. It's actually not. But yes, it looks like one. And it's caused by a similar effect of something flowing there. This doesn't show, but you sometimes will have a deep trench here where you have the subduction occurring. So if this had subduction, if this was sliding down like I drew with the green, then you would have a trench there where the ocean floor is sliding down. Another thing I want to point out, these things here that are coming up, there's interesting features like if you look at the west coast of Washington up to Alaska. Do you know what you see when you look at the west coast? I'm actually going to pull up a map while we're talking. As far as islands. Yeah, somebody is. We don't know who. So if we look at the coast off of Washington, hey, look, it's not allowing me to. There we go. Okay, I think we zoomed out enough. So if we look up the coast here, what do you see as far as the island features?
They're like, I don't know, they're more separated and like have water in between them.
Yeah, they're very broken up.
Very broken up, and they're thin and long, right? At least as was explained to me by Ranger Rick, a ranger program I attended when I was acting up in Alaska. That's because of what we've just been talking about. What's happening there is you had an island in the ocean that was moving toward the continental shelf. And then as the ocean subducts, that material that was the island got scraped off of it. And it's kind of like if you had a nice circular pancake and you're pretty sloppy with your spatula work and you're trying to get it off of the griddle, you kind of squeeze it up and it becomes a long, narrow pancake. That's what caused those islands. They were scraped off. They were ocean islands, and they got scraped off of the ocean plate when it subducted. Just totally cool, I think.
Wait, so the pancake analogy formed the islands that are like broken up?
It formed these islands like these here. All right. Keeping on, you have the abyssal plain, which is not the abysmal plain, but that's always what I think of it as. Abyssal is like into the abyss, the deep. You have a ridge here. What's going on at this ridge? Looking at the picture, you can get some hot tips there.
Oh, that ridge. There is volcanic activity.
Okay, there's a volcano here. What's the general thing that's happening right here? They're getting pushed out by those convection currents we talked about from the mantle. So the mantle material is going like this and like this to push them apart, and then some comes up here and forms new ocean floors. And so that's a mid-ocean ridge, or a, we'll just go with that for now. And notice it does have an offset between the first ridge we see and the second ridge we see. We have a volcano here because, magma's coming up. And there's a place where magma came through. So you'll have vents and things like that along these ridges. And then you keep going along the ocean. So those are basic features of the ocean floor. So the coast, the continental margin means the edge. So that's where you have your continental shelf, your continental slope, and your continental rise. Continental rise is rising up to that slope. Then you have the deep ocean basin, which is the abyssal plain. Like I said, I always think abysmal. These are definitions of those words. I've already defined them. There's no need to define them again. The sea floor is made of basalt because when you have molten magma meet water, it's going to freeze fairly quickly. Not quickly enough to make obsidian, but fairly quickly, so that means that you don't have time for large grains of crystals to grow. So they're tiny crystals, hence the basalt. Talked about all of these things. I like these pictures. These pictures are showing us what the depth of the ocean looks like as you go across it. And you'll notice two trenches here. The Tonga Trench and the Peru-Chile Trench. What causes those trenches?
What do you call it? Or is it where two plates slide away from each other?
It's actually the opposite. Ridges are where they slide apart and you have new stuff forming. So here where it says the East Pacific Rise, I believe that's where you have a rift zone where they're moving apart. Here is a rift zone where they're moving apart. But the trench, the word trench, is for where they're coming together. And you're having something subduct. So you're having a subduction going like this, and that's what creates the trench. Now, does anyone know what the deepest trench in the ocean is? The Marianas Trench, which I always mispronounce. The Marianas Trench has a depth of over 11,000 meters.
That's more
Let's go.
Let's go.
Don't need a submarine or anything.
Yeah, we'll just free diving. Yeah.
That's more than Mount Everest.
That's more than Mount Everest. Mount Everest is something like 8,800 meters above sea level. And the Marianas Trench is over 11,000 meters below sea level. So you could take Mount Everest all the way down to sea level, turn it upside down, and dump it in there, and it'd be completely submerged. Which is pretty impressive. So I thought I had written those in on this slide. It may come up on another slide where I forgot where I put it.
Do you think that there are creatures that can live down there? Because
I do.
that's a lot of pressure.
It is a huge amount of pressure.
They don't know it.
We studied, when we were in physics, we studied how pressure increases with depth. How much depth do you have to go down to go up by 1 atmosphere?
I don't remember.
It was about 10 meters. So just take that 11,000 divided by 10. That's about 1,100 atmospheres of pressure. Right? That is very crushing.
How could a creature adapt to that? Because, I mean, maybe you can breathe down there, but how could they not get just crushed?
Okay, how could they not get just crushed? The key to not getting crushed is to not have solid bone. To be basically a fluid.
So if they're pretty much fluid.
Yeah, so something like a jellyfish.
I see.
A jellyfish, you develop the same pressure inside as outside, and so the differential pressure is nothing. You have the same pressure pushing out as pushing in.
I see.
But if you have something solid like bone, that bone is going to be crushed.
Have they ever been able to put so they haven't ever been able to put any sort of camera or anything like that down there?
I don't think so, no. And that's why I'm saying if we could develop technologies to explore the ocean.
Like,
So,
not even
Do they just know it's that deep because of using technologies like sonar?
Yes. And now I say develop the technology to go down there. You have to develop something that's not going to get crushed down there.
You need like a fluid camera.
Or a really, really hard camera.
Yeah, usually we think really, really hard, but
But I like it.
yeah, I like the way you're thinking. Okay, so ocean trenches are the deepest part of the ocean because what's the reason those ocean trenches are the deepest part of the ocean?
He's just asking a question.
I thought it had to do with the plates going apart or going together though.
B.
Going together is correct. B, subduction. Subduction is what happens when they go together.
I thought that was convergent plate boundary.
That's what it looked. You'd think that.
Subduction.
Subduction, which is where they're converging.
Oh, it's like a type of.
Okay, now this one, a very serious question. I had a student once who had a friend tell him the wrong answer, and we laughed because we knew the answer. But you may not. What causes ocean waves? Okay, we have EE,
Well,
G.
Oh, I think it's egg. I'm just kidding.
It's what?
It's egg.
A.
C.
Yeah.
It's C.
D?
Well,
C?
it's, I know C does because
I think it's
if
C.
you've ever gone
C
sailing, like
all
that.
of the
C
above.
through E.
All of the above.
C3. The answer is C. And I'm glad nobody seriously said A. My friend was at the beach with another, or my former student was at the beach with a friend, and the friend said, just think, all these waves were caused by the ships going out there in the ocean. Looks at him, what did you say? So, remember how we talked about sand dunes and how sand dunes are made? Yes?
Yes.
Yes. Okay, so regale me. How are sand dunes made?
Wind.
By wind moving faster over the surface and slower on the opposite side.
Right. And so it carries the sand up and then drops it when it gets to the end. And so you build up a sand dune. Well, we have a similar thing. Wind blows over water, and if the water's not perfectly smooth, the wind's going to go faster where the water comes up, just because it's going to be compressed there. But when it goes faster, it lowers the pressure. Remember, we learned about Bernoulli's principle: the faster the air, the lower the pressure. And so it lowers the pressure, so it's going to lift it up more.
It's cool how when the air goes over the waves, and the air is trying to do that circular motion,
But
and
it
then
goes fast.
eventually the water follows.
It's more than just that. And I will talk about that in just a moment.
Yeah.
So the wind is what causes ocean waves. If it was ships, then you wouldn't have much going on, generally speaking. Why would somebody get the idea that ships are what cause the waves?
Because when the ship moves, there's more waves.
Okay? When ships move, they create a wave that is a wave. It has a wave going out. It's a shock wave, if you want to be specific. And so if you go water skiing, and that's pretty much your only experience with waves, most of the waves you're seeing when you're going water skiing are caused by the other boats. Some of them are caused by wind, though. Otherwise, it would be perfect glass anytime there's no boat on the lake. But the wind is causing the ripples and whatnot. And so if you're into sailing, you look for the places where you have lots of ripples and stuff on the ocean because that means there's lots of wind there. Cameron had a question, then Hosanna.
Why would it not be the moon?
Okay, why would it not be the moon? The moon would have been our primary answer, not the only answer. G would have been the correct answer. If I was asking about tides, high tide and low tide. So the moon affects the tides, but the waves are not the same as the tides. Okay, Hosanna, what was your question?
I didn't have a question, but I was gonna say, wouldn't also like movements in the earth, like miniature earthquakes, also cause waves?
Yes. That's the textbook, I think, says most waves, so that you have that, an earthquake can also cause a wave, or, boat, and so on. Yes.
Okay, cool.
All right. So characteristics of a wave, and we're going to have to stop with waves for today. You have the crest of the wave. The crest is here, right? You have the trough. The trough is here. The wave height is clearly the distance between, vertical distance between the trough and the crest. And then you have a wavelength. A wavelength is the distance for a wave to repeat. So the wavelength, does anyone remember what symbol we use for wavelength? It's a Greek L, lambda.
It goes down too. It's like a big circular thing.
The motion of the particles do. So you have two different things to think about. The motion of the water molecules versus the combined motion that makes the wave.
Because it's kind of like an iceberg. Like when you measure a wave, like say it's a 6-foot wave, it's actually a 12-foot wave.
Because the water motion below the surface. I could totally buy that. So that's a wave. Now, that's not a breaker. That's not the kind that Bryson was talking about a minute ago. It's not breaking. Question.
Wavelength can also be the distance between the troughs, too.
Right.
Yeah.
It's the distance between repeating. So distance between crests or distance between troughs. Or distance between halfway between the crest and the trough, if you want to do that. Final thing here is the period. We use the letter T for the period usually. Sometimes we'll use P for it. And the period is the time between waves. So if you're at the beach, probably the thing you're most acquainted with, you're relaxing, you're listening to the tide come in, or the waves come in. And so you hear the crash, and then the crash, and the period is the time between those. And for ocean waves, the period, of course, will vary. It's not like a metronome where they come in all at once. So this is what Hosanna was talking about. As a wave passes, now we can see the things we named, the crests, the wavelength. And what you have here, the things that look like clocks, is showing the relative position of a water molecule as the wave passes. So the center on each one of these is where the water molecule would be if there was no wave. But as the wave comes, the water molecules go in a circle. So you can see that there's a circular pattern played out. The molecules went from, if you stay in one place, it's going to go from here to here. And so it's going to go like that, the water molecule. And so the water molecules are doing circles, or they could be doing ellipses, not just circles. It doesn't have to be the same height as the horizontal motion. And as was said by Hosanna, it's going well below the height of the wave or the water level without the wave to where this motion stops. So the wave is passing through more than just above the water. It's also passing below. And when you get to shallow water, we talked about this when we talked about tsunamis. What's the shallow water going to do? it's going to impede the motion down here. So if it impedes the motion, the top tends to go faster than the bottom. And that's what causes you to form something like this, because the top is going faster than the bottom, pulling it forward until it gets so far out that it breaks. So that's typically the cause of breaking. Now, wind blowing will affect it. And it's time to end today. Have a happy Sabbath. Enjoy the alumni weekend.